Today, we're diving into a real scientific detective story. It's a tale about a broken law, a phantom current, and a discovery that totally changed how we see the world and light itself. So, it all kicks off with this simple but kind of profound question. What does happen when a law of physics, something you thought was totally universal, suddenly just breaks? Well, back in the 19th century, that's exactly what happened to one of the biggest ideas in electricity and magnetism.
Okay, so our story starts with a huge problem. See, there was this well-established law, and it seemed to work perfectly, until one day it just didn't.
And this is the law we're talking about, Ampere's law. Now, to put it simply, all it says is that an electric current, charges flowing through a wire, creates a magnetic field around that wire. It was this beautiful, direct link between electricity and magnetism. It seemed to work everywhere, it was consistent, it was the law. So where did this perfect law run into trouble? Well, the problem child was the capacitor. You know the thing, just the simple device with two metal plates separated by an empty space, or maybe an insulator. And when you hook one of these up to a circuit, something really weird happens that puts Ampere's law in a tight spot. Okay, so here's the puzzle. In the wires leading to the capacitor, you've got a normal current, what we call a conduction current. Actual charges are moving. And just like Ampere's law says they should, they create a magnetic field. No problem there. But the real mystery is the space between the plates. There are no moving charges in that gap. It's empty. So according to the original law, if there's no current, there should be no magnetic field. But guess what? There is one. The law was failing right there in that little empty gap. The conclusion was pretty much unavoidable. Ampere's law wasn't exactly wrong, but it was definitely missing something. There was like a ghost in the circuit, a piece of the puzzle that nobody could see. And this is where the hero of our story comes in, James Clerk Maxwell, and his brilliant, almost spooky solution. So Maxwell came up with something totally radical. He said, what if there's another kind of current? He called it displacement current. Now, this isn't a flow of actual physical charges. Nope. Instead, it's this kind of phantom current that just appears whenever an electric field is changing over time. And where does that happen? Exactly in the gap of a charging capacitor. So here's the mind-blowing part. It acts like a current, it creates a magnetic field, but without a single charge ever having to move across that gap. So let's break that down. On one side, you have your good old conduction current. That's real charges, electrons, moving through a wire. But on the other side, you have Maxwell's new idea, the displacement current. No moving charges, just a changing electric field in an empty space. Totally different things, right? But here's the key. Both of them produce a magnetic field. And with that one little addition, bam, Ampere's law was fixed. The inconsistency just vanished. But fixing one law? Oh, that was just the beginning. This ghost current was about to do something way bigger. It was going to unify electricity, magnetism, and even light itself in what has to be one of the greatest aha moments in the history of science. See, Maxwell realized that his new corrected equations predicted this beautiful chain reaction. A changing electric field makes a changing magnetic field. And hey, we already knew from other laws that a changing magnetic field makes a changing electric field. So they just create each other back and forth over and over again in this incredible self-sustaining dance. And what happens when you have this dance? You get a wave, a disturbance that just travels through space all by itself. He called it an electromagnetic wave. And in this wave, the electric and magnetic fields are wiggling at right angles to each other, and they're both at a right angle to the direction the wave is actually traveling. So Maxwell gets to work. He sits down and, using nothing but his equations and a couple of known numbers from experiments with electricity and magnetism, he calculates how fast this theoretical wave should travel. And the number he gets is this one, roughly 300 million meters per second. Now that number was very familiar to physicists at the time. It was the speed of light. And in this unbelievable moment of insight, Maxwell realized his ghost current didn't just fix a broken law. It had revealed the true nature of light. Light is an electromagnetic wave. Think about it. That was the moment everything just clicked into place. The tiny mystery of a gap in a circuit had led directly to solving the centuries-old mystery of what light actually is. It wasn't a tiny particle. It wasn't some weird fluid. It was just a ripple of electric and magnetic fields traveling through empty space. But the story doesn't even stop there, because the theory predicted more than just the light we can see. It revealed that our visible light is just one tiny, tiny part of a huge, invisible spectrum of these exact same waves. And here it is, the whole shebang, the full electromagnetic spectrum. It's got everything from the super long, stretched out radio waves and microwaves through infrared. Then there's that tiny little sliver that is all the colors we can see, all the way up to the really high energy stuff like ultraviolet, X-rays, and even gamma rays. And the craziest part, they are all the exact same thing. They're all electromagnetic waves, just vibrating at different speeds. And you know, this whole spectrum isn't just some cool bit of theoretical physics. It's basically the instruction manual for our modern world. I mean, every single part of this invisible rainbow that Maxwell's theory unlocked is fundamental to the technology that shapes our lives today. Just think about it. The microwaves that let radar systems guide planes safely through the sky, that's this principle at work. And the infrared light that shoots out of your TV remote to change the channel, yep, that's just another form of light that our eyes can't happen to see. And as you ramp up the energy, you get to ultraviolet rays, so powerful they're used in water purifiers to kill bacteria. Then you've got X-rays, which, as we all know, can pass right through our skin to give us pictures of our bones. I mean, that technology completely changed medicine forever. At the super high energy end, you have gamma rays, so powerful they can be used in cancer treatments to destroy malignant cells. And then, way down at the other end, you have those long, gentle radio waves that carry all our TV and radio broadcasts. So, from saving lives to just listening to the radio, it all comes back to Maxwell's discovery. So, what's the big takeaway here? It's that each type of wave carries a different amount of energy. That's the key. That's why high-energy X-rays can see right through you, while low-energy radio waves pass by pretty much harmlessly. Understanding this whole spectrum is what lets us pick the perfect wave for the job. So, let's wrap this up. We started with this tiny little crack in one law of physics. And from there, we ended up unifying electricity, magnetism, and light into this one, single, elegant theory that explains, well, everything from your Wi-Fi signal to the light from distant stars. It really makes you wonder, doesn't it? What other ghosts in the circuit are we just not seeing today? What tiny little inconsistencies in our theories might be pointing the way to an even deeper, more amazing understanding of our universe?